The universe is a dynamic, ever-changing place. It's not static. Instead, it's a vast expanse filled with celestial objects all engaged in a cosmic dance of motion. Stars are born, live, and die. Planets orbit stars. Galaxies, those vast islands of stars, move through the cosmos. Everything is in motion. Imagine a waltz on a grand cosmic scale. Galaxies twirl and spin, their movements guided by gravity. They are drawn to one another, sometimes colliding in spectacular displays of energy and light. These cosmic interactions shape the very fabric of the universe, influencing the formation of stars, planets, and even life itself. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. He observed that distant galaxies were moving away from us. Moreover, the farther away a galaxy was, the faster it seemed to be receding. This observation led to a profound realization. The universe is expanding. Imagine dots on the surface of a balloon. As you inflate the balloon, the dots move farther apart. Similarly, as the universe expands, the space between galaxies stretches, causing them to move away from each other. Hubble's discovery was a paradigm shift in cosmology. It challenged the prevailing view of a static, unchanging universe and provided the first observational evidence for a universe in motion. His observations laid the foundation for the Big Bang theory, which describes the origin and evolution of the universe. The expansion of the universe is not constant. In fact, in the late 1990s, astronomers made another startling discovery. The expansion is accelerating. What could be causing this accelerated expansion? The answer, it seems, lies in a mysterious force called dark energy. Dark energy is a hypothetical form of energy that permeates all of space and exerts a negative pressure, pushing everything apart. Imagine dark energy as an invisible hand, constantly pushing the galaxies farther and farther away from each other. It's a force that opposes gravity, counteracting its pull and driving the accelerated expansion of the universe. Dark energy is one of the most profound mysteries in modern science. Understanding dark energy is crucial for understanding the fate of the universe. The discovery of dark energy has led to several theories about the ultimate fate of the universe. One possibility is the Big Freeze. In this scenario, dark energy continues to dominate the universe, pushing galaxies farther and farther apart. As the universe expands and cools, stars will eventually die out, leaving behind a cold, dark, and empty cosmos. Another possibility is the Big Crunch. In this scenario, the expansion of the universe eventually slows down and reverses. Gravity takes over, pulling everything back together in a colossal collapse. This would be the reverse of the Big Bang, ending in a singularity of infinite density and temperature. A third possibility, perhaps the most dramatic, is the Big Rip. In this scenario, dark energy becomes so strong that it overcomes all other forces, including gravity, and the forces that hold atoms together. Determining which fate awaits us depends on understanding dark energy and its properties. While the universe as a whole is expanding, galaxies are not just drifting passively through space. They are engaged in a complex gravitational dance, their movements influenced by the distribution of matter and energy around them. This cosmic ballet often leads to spectacular collisions and mergers. One such collision awaits our own Milky Way galaxy. In about 4 billion years, the Milky Way is destined to collide with our nearest galactic neighbor, the Andromeda Galaxy. As the two galaxies approach each other, their gravitational forces will distort their shapes, pulling out long streams of stars and gas. The galaxies will pass through each other multiple times, their stars and gas clouds interacting before eventually merging into a single, larger galaxy. The collision of the Milky Way and Andromeda is a reminder that the universe is a dynamic and ever-changing place. While dark energy drives the accelerated expansion of the universe, another enigmatic entity plays a crucial role in its structure and evolution: dark matter. Dark matter is a hypothetical form of matter that doesn't interact with light or other electromagnetic radiation, making it invisible to telescopes. We can't see dark matter directly, but we know it exists because of its gravitational effects. It interacts with ordinary matter through gravity, holding galaxies and galaxy clusters together. Without dark matter, galaxies would fly apart due to their own rotation. Imagine dark matter as an invisible scaffold, providing the gravitational framework for galaxies to form and evolve. Dark matter is estimated to make up about 85% of the total matter in the universe, dwarfing the amount of ordinary matter. While we don't know what dark matter is made of, its presence is essential for understanding the large-scale structure of the universe. The interplay between dark energy and dark matter determines the fate of the universe. The expansion of the universe is a mind-boggling concept. It seems to suggest that everything is moving away from everything else with no end in sight. But are there limits to this expansion? Are there regions of space where it doesn't hold sway? The answer, surprisingly, is yes. The expansion of the universe is not uniform on all scales. While distant galaxies are receding from us, objects that are gravitationally bound, like stars within a galaxy, planets within a solar system, or even people on Earth are not expanding away from each other. Imagine a raisin bread dough rising in the oven. As the dough expands, the raisins move farther apart. However, the raisins themselves don't expand. Similarly, while the space between galaxies expands, the galaxies themselves, held together by gravity, do not. Gravity plays a crucial role in shaping the local structure of the cosmos, creating pockets where the expansion is negligible or even reversed. To understand the current movements and ultimate fate of the universe, we must look back to its earliest moments. The Big Bang Theory, our best model for the origin of the universe, describes a hot, dense, and rapidly expanding state from which the cosmos evolved. In the first fraction of a second after the Big Bang, the universe underwent a period of rapid inflation, expanding exponentially. This inflationary period left its imprint on the cosmos, creating tiny fluctuations in the density of matter and energy. These fluctuations, amplified by gravity over billions of years, became the seeds for the large-scale structure of the universe we observe today. The galaxies, galaxy clusters, and vast cosmic voids are all remnants of these primordial density variations. The early universe also left behind a faint afterglow, the cosmic microwave background radiation. Studying the cosmic microwave background radiation and the distribution of galaxies allows cosmologists to probe the early universe and understand the processes that shaped the cosmos into its present form. The universe, like all things, is finite. It had a beginning, and it will have an end. While the exact nature of this end remains a mystery, our understanding of physics and cosmology provides some clues about what the universe's final act might look like. As we've seen, dark energy is driving the accelerated expansion of the universe. If this expansion continues unabated, as seems likely, the universe will become increasingly cold, dark, and diffuse. Galaxies will drift farther and farther apart, becoming isolated islands in an ever-expanding void. Stars will eventually exhaust their nuclear fuel and die out. Black holes will evaporate through Hawking radiation, a slow process that will take trillions of years. The universe will become a cold, dark, and desolate place. This is the essence of the Big Freeze scenario. Regardless of the specific scenario, the end of the universe is an inevitable consequence of the laws of physics. While we've learned a great deal about the universe and its evolution, many questions remain unanswered. The nature of dark energy and dark matter, the ultimate fate of the universe, and the possibility of other universes are just a few of the mysteries that continue to challenge cosmologists. What is dark energy? Is it a cosmological constant, a property of space itself? Or is it something more dynamic, a field that evolves over time? What is dark matter made of? Is it composed of weakly interacting massive particles, sterile neutrinos, or something else entirely? Is our universe unique, or are there other universes out there, perhaps with different laws of physics? The quest to understand the universe and our place within it is a journey of discovery, one that will likely continue for generations to come. Reflecting on the vastness of the universe and the cosmic processes that govern its evolution can be both humbling and awe-inspiring. It reminds us that we are part of something much greater than ourselves, a grand cosmic narrative that has been unfolding for billions of years. While the universe may have an end, life, in some form, may find a way to persist. Perhaps new universes will be born from the ashes of the old, continuing the cycle of cosmic evolution. Our understanding of the universe is constantly evolving as we make new discoveries and refine our theories. In the face of the vastness of the cosmos, we can choose to feel insignificant or empowered. We can marvel at the beauty and complexity of the universe and embrace our role as curious explorers, seeking to comprehend the grand narrative of which we are a part.